Let me a new project.
Like this is CSC450.
Why?
CSC450 chat server.
I'll just create a directory or something. All would be good. All right, and then we have this guy. All right, so we were talking about datagram versus stream sockets last time. One is the UDP protocol, follows the UDP protocol. One follows the TCP protocol. What's the difference between those?
Stream sockets are what happened last night with you.
That's right. So what's the difference between UDP and TCP? Okay. And then TCP is resends, guarantees it gets there, blah, blah, blah. Much more overhead, but with some guarantee, so we have to decide which application it's going to apply to. So what do you think? If we're writing a chat server, what are the pieces that go into a chat server? Let's think about that kind of here at the high level. And the reason I like using chat servers as our example is when you initially consider a chat server, we think that that's kind of, oh, that's old technology, must not be very difficult, blah, blah, blah. But the reality is that there's quite a bit of complexity that goes into a chat server, to the point that if you need to add chat functionality to an application today, it actually makes that application substantially more complex. Because now you need to find a place that, A, you can host your chat server code on. How many simultaneous connections do they allow to have open? So the second the world gets bigger, that we have all this inter-process communication across the internet, now other people want to start making money off you. So when you want to be able to run that many open connections, you got to start paying somebody for server time. So we're going to fake it, but let's, well, not completely fake it. We'll have some model. But we're going to have our server here in the center rather, chat server. And we're going to have multiple clients connected to this. Do 3 of them for right now. All right, so all 3 of these guys are going to connect to that chat server. And we mentioned last time with our stream sockets that this server is going to effectively bind to a local IP address and bind to a port. Then it's going to accept an incoming connection, which establishes a two-way communication channel. And then, if he wants to listen for another incoming connection, he has to go back and listen for the phone to ring again. So we're going to have to spawn off a child to go and deal with that. But we'll get down to that. We'll get down that path here in a few minutes. Okay, so we have 3 incoming connections. Every single time these guys connect, a socket is born. Okay, so we'll call this guy P1 sock, P2 sock, and P3 sock. We're going to have to store these or collect these somewhere so that we can use them, but for right now, we'll just arbitrarily lay them over here on the side and just say, when these connections were established, and these are going to be two-way communication channels for our big picture here, these 3 open socket connections are now established. So if P1 sends a message, it's sending it over this stream socket to the chat server over P1 socket. Now, typically when we think about chat servers, or at least our initial kind of global chat server, everything's a broadcast, right? So when P1 sends a message, P2 and P3 should all see it. These are broadcast type things. So when P1 sends a message over P1 sock, and we use universal I/O for the chat server to read from that, the chat server then needs to go and rebroadcast that over P2 and P3 sock. So all other sockets other than him, which means we need to store these guys somewhere. How do we access these sockets? So when a socket is created, P1 sock, P2 sock, P3 sock are created. What are the data types of these 3 things? Okay. But even simpler, these are file descriptors, FDs, which effectively are ints. So these are all file descriptors, integers in universal I/O. So we really would just need to store an array of integers to hold on to all of our constant sockets, all of our currently connected sockets. All right, so let's start off by establishing a single connection. They don't give us an example, we'll just open up and do it in the, pretty sure they gave us, yeah, here's our stream socket. So here's our passive socket, here's our active socket. So we have our server, sets up a socket, it binds, we receive from it, we send to, okay, we don't want datagram sockets. So let's just go out here. And let's open up our bash shell. Okay, so create an endpoint. So this is socket types.h and socket.h. Here's our domain for our socket. We need to bind to a point. So then get address info. Back here. All right, so we have our socket, we have our domain, we have our type, we have our protocol. The different domains, this is local on a machine, this is over the internet using IPv4, this is over the internet using something nobody uses yet. We have our stream sockets. So let's go ahead and open up our initial socket, this guy right here, but we need a listener. This didn't move so much. I think I need to stop scrolling. All right, so it's going to return an int, which is our file descriptor. It's going to take in a domain. Here's our examples of domains down here. So we're going to say af_inet, okay, and that comes from types.h. Then it's going to take in a type. Let's get down to type. All right, so that's sock non-block. Type argument serves as a second purpose. In addition to specifying a socket type, it may include the bitwise or the following values. So whether we want it to be non-blocking or block on each direction. Is there something above there? Okay, yeah. So here's the higher level socket type, which is either going to be stream or I completely hate the scrolling on this. Stream or datagram. So we have our sock stream for type, sock datagram. We've decided we're going to use streams. So that's the TCP thing, because we certainly don't want to lose chat messages, right? All right, finally, we take in a protocol. So let me run this again so I can keep down here. All right, protocol specifies a particular protocol to be used with the socket. Normally, we only use a single protocol, blah, blah, blah. Socket streams are full duplex byte streams, similar to pipes. They do not preserve record boundaries, blah, blah, blah. So what are my options for? That's for type. That's for type. Let's see, specifies a particular protocol to be used with a socket. Normally only one single protocol exists to support a particular socket type within a given protocol family, in which case protocol can be specified as a 0 to just use the default. However, it is possible that many protocols may exist, in which case a particular protocol must be specified, blah, blah, blah. So for us, we probably wanted to use just 0. Typically, we also want to have a address this is going to bind to. Ah, there's the bind. Okay. So we're going to create our initial socket. So let's just open up I'm going to steal this pipe example code. We'll just say, we'll grab all this for right now. And we're going to create a new file here. Actually, I could do that over here, right? So this is going to be socket example.c. Save. Paste some stuff in. There's that. Let's go back in here. We need to bring in socket.h and types.h. We already got types.h. So there's our socket.h. All right. So now we'll go ahead and create our initial socket. So we're going to call the socket function, passing it a domain. So we're going to say af_inet. So int fd is equal to socket. Hey, I want to keep switching over to that. af_inet. This guy. And then we need to pass it a type. So sock_stream. That's the type of socket. And then a 0 for default protocol, which will be TCP/IP. All right, so that's going to give us our file descriptor. So now let's go back to this chart that tells us the generalistic steps. So we need to bind next. Let's just get down here to the thing. So we just created our socket, so we're right here. Now we're going to bind to something, and then we're going to listen, ultimately accepting something that comes in. So let's go look at the bind function. Okay, lives inside of socket.h. Here's the function. So this takes in a sock file descriptor, which we currently have. It takes in a socket address struct. So this is a sock ADDR. And then it takes in a address length. That's going to be maybe weird for us, but okay, let's. So we already have our file descriptor, so let's start building our thing. And notice that bind also returns in so let's call this guy sockfd, just to keep these separate. Then we'll say int bind fd is equal to bind, passing it sockfd, then passing it some more stuff. What comes in next is our sock address. So let's look at that guy. So here's a sock address that takes in address family and then the actual data. So we're going to have to look at sock address structure. And what else does it take? Lastly, it takes in a socket length type. Okay, so let's do this. Man, socket. Oh, that's beautiful. All right, socket is created with socket that exists in the name space address family, but has no address assigned to it. Bind by the file descriptor sockfd. Address length specifies the size in bytes of the address structure pointed to by address. Traditionally, this operation is called assigning a name to a socket. It is normally necessary to assign a local address using bind before a sock stream socket may receive connections. The rules used in name binding vary between address families. Let's see, for information for AFC IP7, the rules associated with name binding. So we need to look at IP7. Of course, it gives us an example for AF Unix, the one thing that we said we probably would never just use. Let's get back down to that. An example using bind for, okay, so we want this guy. Okay. Effectively, what we're getting is we're getting the IP address and the port that we want to bind to. Okay. So here we go. GetAddressInfo returns a list of address structures. Try each address until we successfully bind. All right. That sounds like a Craigslist thing. If socket 2 or bind 2 fails, we close the socket and try the next one. All right, so let's see, where is our let's go back down to so GetAddressInfo is going to return a address that can be given node in service which identify an internet host in service. GetAddressInfo returns one or more address info structures, each of which contains an internet address that can be specified in a call to bind. The GetAddressInfo function combines the functionality provided by getHostByName and getServerByName functions into a single interface. But unlike the latter function, GetAddressInfo is reentrant and allows programs to eliminate IPv4 versus IPv6 dependencies. Okay, so the address info structure used by contains the following fields. So we get flags, family, socket type, protocol, address length, which is the thing we need, and then the actual address, which is the thing we need. So all that other crap we don't actually need. Let's see. Incoming and outgoing host names to be transparent. But GetAddressInfo is returning an int, right? I think that's what we want. Let's go down to the bottom here. There, get sock name, listen, socket, GetAddressInfo. just do this. See if we can get the Linux socket bind. Do we have to pass it the entire? Alright, so there's our socket we just created. Here's our socket address constructor that's going to come from, it's probably in socket.h. So we're zeroing out this memory address for the right size of our socket address. We're going to set our family to AF. Was our AFNet? INET. Okay, that's not going to do anything. Then we're binding to the add address. So add address gets set. ADDR gets set where? Gets set to a bunch of zeros right here, up to the size of our socket, giving it the address of address, this guy. Then we set the family. Then we're passing it the path of. That's for, yeah, this example's for Unix ones. That's not going to work for us. Bind INET. I think this is where we're going with this. All right, so here's our socket address. We can give it its name. So I'm going to steal that, and that guy, pretty sure is going to come from socket.h, like I said. Let's go back here. All right, so that's going to be the name of our socket that we're going to be binding to this. Then we set a couple of the parameters for that guy. So we're going to set it to AF INET. We're going to give it a specific port. And where do I set port up here? So H10S, let's copy this. Go and do a man on that. Okay, so this converts bytes between host and network order. So where are they getting the original values here? Where did port come from? Oh, it comes into this function, make socket. All right, so we're just going to give it a port. And this guy is just to stay consistent with that, we'll create our port to be the same type. So we're going to listen on port 3000.
So what does that mean?
What do you mean?
That we're listening on port 3000?
Think of a phone system. So when you dial a phone number, then sometimes there's extensions.
Okay.
The phone number is the IP address. The extension would be the port.
Okay.
I think that's as good of a way as any to explain it. So on an individual operating system, depending on whether, how new the operating system is, historically they were 16, it was 2 to the 16th, actually 2 to the 8th in really old ones. Number of unique ports, I think today they're 2 to the 16th or 2 to the 32nd possibly. You might have 4 billion ports, but it's probably 65,535 unique port, 65,536 unique ports today. And the first 1,024 of them, 0 to 1,023, are reserved by the operating system, so they're in actually protected memory, or I guess kernel space in modern OSs. So we have to choose a number between 1,024 and quote infinity, whatever the maximum port is on that that guy. So that's why we just randomly pick 3,000. If you've ever run a third-party web server or something on your machine for testing, a lot of times the default port is 8080 because the default HTTP port is port 80. So 8080 is an easy way to remember that extension. So I just randomly chose 3,000 as our port. All right, and then we need to convert that port into, so we have our, I'm going to steal these guys right here.
The most commonly used port 3000 is used for the Trojan INET spy.
See? Is that really the most commonly used port? I think we just proved it in class.
Most commonly used program for the port 3000.
Oh, okay.
I feel like an antivirus might block that.
Okay, so this converts our port into, what does it need to be in that format? Tons. So this is host. So these all these libraries that have a TO in the middle, this is conversion stuff. So this is converting from host to network byte order. I'm not sure why there is necessarily a difference. Maybe it's just because it's an old. Because the TCP/IP stack should allow standard ends, but I guess whatever. Okay, so we need to do the conversion to get our integer port in there, or int-like port into the correct format. And let's see, then this guy, he's got to be some sort of grab the local. It's INET address any, so that's not binding it to a single IP. It's probably just binding it to the local IP. Yeah, this is a so-called IPv4 wildcard address. It's useful for applications that bind internet domain sockets on blah, blah, blah. Let's look at this. What if I want to bind to a specific local address? Oh, it binds it to all the available interfaces. That's actually somewhat helpful. So on your operating system, you might have, for example, on your laptops, you have a Wi-Fi network interface port, and then you also might have a wired network interface port. Those are two different interfaces. You might be on two different networks, potentially. We're going to be binding this program to listen on any of those devices. So that's what we're doing as opposed to a single thing. We could also, it looks like, we could set the address to be this is what we talked about last time, the loop back address 127.0.0.1. So we can bind it to both all the things or just that one address. So this is how we would do it if we wanted to build an IP address out of a string version of an IP address. But this guy is basically saying we're going to bind to localhost on any of our ports or any of our interfaces. All right, then here's where we actually do the bind. All right, so I'm going to steal this, and we don't error check our code, so. Why error check when you could just not? Did it?
Really? They told me it was okay.
I hope he didn't say that. It's like, well, you know, I've never really found a use for error checking. I mean, I'm not saying it'll never happen, but at this point I haven't made an error.
You teach us to write perfect code here, so obviously you'll hit it.
It's like, we don't need error checking. I mean, heck, half the time I don't even turn the monitor on. These stupid laptops today, you can't do these. I mean, I pretty much, when I sit down to code, I have to turn on the power settings to just dim it to the point where it's not bugging me. I don't really need to pay that much attention to the output since there is none. You know, at least on the error console. All right, so we're going to bind to our socket FD, or sock FD. We're going to convert our name, which is this guy up here. So we're going to take the address of name. That's the do we did here. Take the address of name, convert it to a struct sock address pointer. This is actually kind of weird. Oh, okay. Actually, this is interesting. This is interesting syntax. Remember how when we first talk about pointers in some of the early programming classes, we talk about how Java, when they took away structs, they took them away thinking that a class without methods is equivalent to a struct, and it's only sort of like a struct. Or a class without method, by default, objects in object-oriented languages are passed by address. Structs are passed by value. Okay, so when we create this struct right here, we're creating a variable name of type sock address in. All right, so this guy is a struct, but we should think of it like a primitive type, like a normal int. All right, in terms of how it might get past the stuff. So now we're setting those various parameters. So notice this guy kind of looks like an object at this point because a struct is effectively an object without methods. So we're setting the properties of this struct. But now our bind, so let me go back here and do man bind just so you can see this guy takes a struct, a sock address pointer. So a pointer is a variable capable of holding a memory address of a sock address. Make sense? That's what it takes as a parameter. Well, we don't have a pointer to it. We have an actual primitive type socket, or actual primitive type struct. So we come back in here. This is our primitive type. We're saying give me the address of that primitive type, which at this point is just a generic plain Jane address. It's completely arbitrary. We don't know that it's associated with a certain kind of struct or an integer or a string. We don't know what it's associated with it. It's just a memory address, some crazy hexadecimal looking thing. All right. Now we're typecasting this back to a struct sock address pointer. So we're giving some semantic meaning to this memory address so that basically bind FD won't complain, or bind rather won't complain on its second parameter because it's expecting something of type sock address pointer. Make sense? And it's all because this guy initially acts like an int, not a pointer, where an object would act like a pointer. All right, so we'll pass it our file descriptor for our socket. We'll pass it our sock address pointer, and then ultimately the size of that guy. So that's going to close here. I'm missing a closing guy like that. And you've probably seen this size of function before as well. When I first teach arrays, and we talk about how arrays are fast because we, like bucket 3 is actually the base address of an array plus 3 times the size of whatever the type is, like size of int. So size of int in Java would be 4 bytes, 32 bits. All right, so size of is a function that gives us the size of a particular type. So this is going to say, what's the size of a sock address, the size of this particular guy? What's the address of him dressed up to look like a sock address pointer? And then, Abe, you probably thought I was going a different direction with the dressed up thing, right? Yeah, I saw it in your eyes. And then then we have our socket file descriptor. All right, so now we have bound, we still have not started listening for an incoming connection. Okay, we created a socket file descriptor. We gave it a name. Effectively, we've said, okay, we've taken this generic socket descriptor, we've bound it to local stuff, a local IP address, local ports, that kind of stuff. All right, now we actually need to accept an incoming connection, so we need to listen. All right, well, let's just go back here to this guy. So now we're going to listen after we bind. Come in here. Okay, so here's the listen function. Takes a sock FD and an int backlog. That's probably just a file descriptor to a log file. Defines the maximum length to which the queue of the pending connections for sock FD may grow. If a connection request arrives when the queue is full, the client may receive an error with an indication of econnection refused. Okay, whatever. The underlying protocol supports retransmission like TCP/IP does, so we would be fine. The request may be ignored so that the later reattempt of connection succeeds. All right. So what should we pass it as a backlog? Maximum length to which the queue of pending connections for sock FD may grow. All right. Till you just run out of, let's see, do they give us an example of maybe what we should use? Nah, we'll just use 100. All right, so we'll listen. Again, it's going to give us a file descriptor. Int listen FD is equal to listen, passing it our bind FD. Actually, we would pass it the socket FD. When we first passed this guy in, we were wrapping it. And then
You want to pass the address of the socket, not the actual socket?
not for listening.
Sure.
I'm pretty sure. Yeah, what's the file descriptor?
Yeah, you're just passing it the file descriptor, you're not passing it.
That refers to a socket of type socket. Yeah, no, we're passing it the socket. When we listen, we're passing it the file descriptor to the socket we're going to listen on. And that socket file descriptor has been modified based on the bind command. I mean, effectively, we're listening to an address, but we're listening to it indirectly through the socket. So sock FD, and then we said 100 connections.
Sock FD, not socket FD.
Yeah. All right. Then we need to actually accept an incoming connection. So this guy blocks until a client actually connects. So next thing, let's go ahead and just say printf. Listening \n, and then we'll say well, let's just do this here. Accept. So the accept command takes in, it's called accept for. Oh, here's just accept. Socket FD, socket address, and then the length of that address, that'll accept the incoming connection. So we'll call this client FD for accept. client FD is going to be equal to accept, passing it sock FD, passing it this same thing. Well, actually, basically just both of these guys. And then we'll prove a client was connected by saying client connected. Accept sock FD, there's that, there's the size of, that all that guy takes. Socket length, address length, okay, yep, that should do it. All right, so we'll save that. Go back out here. And this is our socket example, GCC socket example. Let's see, where'd that guy come from? Of course it's not. So unsigned int 16 type, we probably just say int. And bind systypes.age, we already have that, right? There's socket, we don't even need the interprocess communication stuff. Where does socket address live, man? What other libraries do I need to include for those? Let's just do this. We'll do this, and we'll ask what the header file is. Unix socket library. Well, at least that was incredibly helpful. Here we go. The NetI /nh. Obviously. All right, passing argument 3 of accept makes pointer from integer without a cast. That's just a warning. Was that still a warning? Oh, one warning. Okay, yeah, that builds. All right, so it's listening, completely spelled wrong. And then we need another console. If I open up another console, is it going to close my first console? Is that, I just do this for a new one? New terminal. And we want to go to port telnet localhost 3000. Oh, I don't have a telnet command? Nice. Really? Hold on. Huh? Yeah, it's blocking. It's blocking waiting for an internal connection, but I don't have a freaking, I have to write another client application to actually connect to it. All right, so we'll start here on Monday. We should be able to test this. I don't know if there's a way for us to get the local IP address. This is probably behind a firewall. But in any case, we should be able to now connect to that listening socket and at least get a client connected. Let's just see here real quick. Right,